we proceed with the next presentation, and that will be given by M.M. Khan, who is a PhD student of Professor Iqbal from IIT Roorkee, and the name of the presentation is High Strain Rate Loading on Concrete Under Compression Using Split Hopkinson Pressure Bar Overview.
So it's my pleasure to have my first APM conference, and I am Mohammad Mohsin Khan from IIT Roorkee, India, and my supervisor is Dr. Mohammad Ashraf Iqbal, the professor in the same institute IIT Roorkee. And then my topic is that high strain rate loading on concrete under compression using the SHPB. So I have overview on the some literature that has been researched on this topic, and find out some conclusion that I will try to explain here. So first of all, I will tell you something about this background, that impact study have traditional focus on the military application, impact loading on incoming missiles or other sources on the protective cells of nuclear power plants and important structures. Then dynamic loading also come from the natural hazards like the tornado, earthquake, ocean waves, etc. Also important for high load or high strain rate loading. And it is also developed interest have arise for high strain rate events, including the collision of automobiles, impact design for air and space vehicles, blasting, as well as process involved in the manufacturing of the material. So these vehicle impact, missile impact, projectile or aircraft impact, protective layer of nuclear power plant, runway, which is the example of repeating loading, are responsible for the high strain rate loading. Nowadays, there is an increased interest for the engineer to provide the design to withstand impact and design, impact and blast loading, mostly for the critical infrastructure protection throughout the world. The material under the high strain rate loading show the complex behavior when it is subjected to high strain rate loading. Therefore, the study of dynamic response of material is more important for structural engineers to analyze and design the structure for their safety and security purpose. So, in order to analyze the dynamic characterization is a description of feature for some or something under dynamic loading. So our main focus in this PPT is on the strain rate, or which is defined as the strain rate is the change in the strain oblique deformation of the material with respect to time. Now there are many methods of techniques that have been developed previously, which is used for the high strain rate loading. Out of them, these are some I have listed: the drop weight, ballistic impact, SHPB, tailor impact test, plate impact test, and the material on which these methods mostly used are steel, concrete, composite material, ceramic, or polymer. There are some alternative method also used to find out the response of the material under this high strain rate loading by using some numerical tools for the simulation. These may be the Abacus, LF Dyna, ANSYS, or Autodyne. So out of this, I have focused on the instrument that is SHPB, split Hopkinson pressure bar test, which is used for high strain rate loading. It is also called as Kolesky bar, apparatus for testing the dynamic strain rate, which is dynamic stress strain responsible of material. It is the way to measure the stress pulse propagate in a metal bar, and this can be used for the characterization tool for the mechanical response of the material deforming under at high strain rate, which is in the range of 10 to 10,000. Here the strain rate can also be explained the ratio of the deforming speed of specimen divided by the specimen length. This tool is mainly used for tension, compression, bending, and torsion testing. It is depending upon the loading condition and the specimen gripping method. Although principles for the test measurement are same. Here the parameter that will be we will calculate is the DIF. DIF is called dynamic increase factor, which is the ratio of dynamic uniaxial compressive strength to the static uniaxial compressive strength. Here I have put a schematic sky compression bar apparatus diagram. The working is that in this diagram you can see a striker here, and which is loaded by using a gas gun, which hits on this end on the incident bar. This generates a pulse which propagates in this bar and measure at the middle of this bar. The wave is referred as incident wave. The wave again propagates incident bar. At this point, some waves get reflected back and some waves transmitted through the specimen into the transmission bar. This is mainly due to the difference in the mechanical properties of incident bar and specimen. Now, the waves that incident and reflected are measured at the center of incident bar with the help of strain gauges mounted on the surface, and the transmitted signal or transmitted stress pulse are measured by the strain gauge mounted at the center of transmission bar. Then we have a Wheatstone bridge to convert this voltage into the strain time graph, which is connected to the data processing unit in the last for analyzing the stress strain time graph. Now, this is the component of SHPB that I have divided into three parts: the loading device, bar component, and DARF term, which have these different components: the pressure vessel, actuator, compressed barrel, striker. That I will skip this. Now, the working principle on which this split Hawkinson pressure bar apparatus work is that you can see here the wave which is travel in this incident bar when it hits to the incident bar is measured as incident wave, which is represented epsilon I. The reflect wave which come after the reflection from the interface from specimen and incident bar are measured again by the same strain gauge on the incident bar, which is termed as the reflected wave. Now the transmit waves are measured at the transmission bar by using the same strain gauge. Now you can see clearly that these are striker bar, incident bar, and transmission bar, and specimen is sandwiched between the incident bar and transmission bar. Due to difference in the mechanical properties of this specimen, the wave coming in the incident bar gets reflected back, and some is transmitted through the transmission bar. So by using the one-dimensional elastic wave propagation theory, the Hooke's law, and equilibrium condition in the specimen during failure, we have obtained these following relationships, in which these strains in the specimen, strain rate in the specimen, and stresses developed in the specimen are calculated with the help of the property of bar. And in this paper, what I observed that many researchers work on this DIF, dynamic increase factor ratio. The different researchers give the different equations based on their experimental data or experimental observation. And some researchers also give the same concept for the mortar or some other concrete like brittle material. So this is the first. You can see here the equation which is given for DIF is the ratio of the static and dynamic strain rate. But you can observe they also give an end transition point. The transition point is the point where the response of the material become more sensitive to the strain rate. But before that, the behavior of material is not that much sensitive. But after the transition point, the response of the material becomes too much sensitive to the strain rate, due to which they have given the another equation which is above, especially above the transition point. And these you can observe that DIF above the transition point is mainly empirical equation using the log equation. The many researchers give the equation, empirical equation for the DIF, but these are some important DIF equations which are used in the design of material model, the design of material model. And this is the comparison of the equation which is given by the various researchers. Here you can observe that after the transition point, the response of the material is highly sensitive to the strain rate. Here we are observing mainly the strain rate effect on the dynamic properties of the material. And these strain rate effects become more dominant as we increase the strain value more than in the order of 100. Below that 100 strain rate order, the response of material is not too much sensitive for the DIF. And on the basis of this graph, I have find out that some conclusion, and that conclusion is that the concrete which are subjecting or any other mortar or concrete light weighted material which are subjecting to the high speed impact loading, in that case, it is observed that most of the researchers represent that the lateral inertial force of the specimen increase, and this inertial force increase the lateral inertial confinement in SHPB test. This lateral inertia effect resists the expansion of the specimen in the radial direction under the high strain rate. Hence, there is a rapid increase in the dynamic material properties of material which are subjected to the high strain rate beyond the transition point. But there are very some few researchers who define these transition points. Next one, the lateral inertia confinement increase the load carrying capacity as well as the dynamic increase factor under the compression at high strain rate. However, it is also observed from the above study that there is a dramatically change in the DIF for the concrete like material from the transition point. And the main reason which is given that is the inertial force or inertial effect. Except to this, there are many other possible effects that may be the end friction effect that will try to restrain the expansion of specimen at the interface of material and the bar. Another important conclusion that may be possible that the generation and propagation of the crack in the hardened material increase the energy absorption capacity of material under the high strain rate loading. Therefore, timely dependent growth of micro and macro cracks in the hardened concrete may also contribute to the strain rate dependent strength enhancement of the concrete. Thank you for your attention. If you have any query,
thank you very much for this fantastic presentation. Well, can I ask a first question? So obviously this information about dynamic strength of concrete is of extreme importance for seismic protection, because if you want to protect structure, we need to know how will that behave in terms of strength once some dynamic loading like seismic loading is coming. How do you think can these constitutive relations that you evaluate in conditions of one-dimensional loading, uniaxial loading, how these can be applied to predict behavior and strength of structure under three-dimensional, real three-dimensional loading?
Actually, the SHPB working principle is only based on the one-dimensional elastic wave propagation. If we will go further to this experiment in case of like a scalar impact or plate effect test, in that case, the 1D test wave is not possible. But the working principle of this SHPB is only based on the one-dimensional elastic wave propagation. The equation that we derive is only for the one-dimensional elastic wave propagation.
Okay, then you will probably need to somehow tune constitutive equations. Thank you very much. Questions?
Sorry, I have a question regarding your constitutive model for dynamic problems. I'm not sure whether you know or not about fiber constitutive models for structural elements like for beams and shells. Is it possible to use your model and modify it for the usage with these fiber models for structural elements?
Actually, here what I want to explain that DIF, dynamic intrinsic factor that they develop is mainly related to the strain rate. And this empirical equation can be used in development of the material model, which is implemented in the numerical tools. For example, if we will go through this RHT model, in that RHT model, there is an empirical equation which is given by the CED. It's totally based on the standard effect. So here, these the equation developed based on the experimental mainly, and that is validated with the help of simulation.
Okay, thank you.
Thank you. More questions, please. Okay, if there are no questions, we should thank Mr. Khan for this very interesting presentation. Thank you very much.